work at KWR and TU Delft, and I'm going to tell you about the pilot that we do at Deltares, together with Naked Energy, who is the producer of the PVT panels that we use. Well, we have seen this picture already a couple of times now today in the various forms. But I want to show to you it again, because one thing is very important to realize when we use ATES, when we use storage. During summer we are cooling the building with the groundwater. But while we are cooling the building, at the same time we're actually storing heat in the warm well. And during winter we're going to reuse that heat again for heating purposes. And while we are heating the building, we are again storing cooling capacity. So when we want to use this system, the building energy demand profile should balance between heating and cooling demand. We need about as much cooling demand in the building as we need heating demand, because otherwise we're either depleting the cold well after a number of years, or either depleting the warm well after a couple of years. But yeah, you probably all know or may expect that there's no building that exists that have an exactly balanced heating or and cooling demand. So there's a challenge, and that was one of the barriers also, that is imbalance in heating and cooling demand. How can we overcome that? Well, in the Netherlands currently, most of the buildings have more or less energy balance like this. A very large heating demand, small cooling demand that is shifting a bit due to climate change and improved insulation standard. This cooling demand is increasing a bit, and this heating demand is decreasing a bit in buildings in the Netherlands. But in other countries this may vary, and also depending on the type of building that you have. For instance, in the Netherlands, the houses have a much larger heating demand compared to, for instance, offices or hospitals. So in the Netherlands currently this excess of heat that is needed is often produced by natural gas-fired boilers, and that's something we don't want to use anymore, as we all know. So what we propose in this pilot study is that we take some heat from the sun to match the heat capacity that we need for heating in the winter time. So we're going to take some heat from solar panels, put that in the warm well during summer, and then we can in winter we can use that again for heating purposes. Well, we tried that. We are currently trying that at the Deltares office buildings in Delft. Deltares already has an ATES system running for a couple of years, and just a couple of weeks ago we connected the solar collectors to the ATES system to gain extra heat for the ATES system. To give you a bit of an overview, the building that you just saw, this nicely shaped building, is more or less a star. It's this building, and that is connected to a cold well and a warm well over here. And this location, that's where the solar panels will come. And this is a very large facility for all kinds of tests that Deltares carries out. And that's important because this building has a very high heat demand, which is now currently not connected to the ATES system yet, or was not connected to the ATES system, but this is now heated by natural gas-fired boilers, and we want to reduce the use of those boilers by connecting it to the ATES system and provide that building from sustainable heating. So this is a bit more in detail. Here are the cold and the warm wells, some observation wells, and these are the solar panels which have been installed a couple of weeks ago, and they are connected. This location here, this this aerial view is not up to date anymore, but these are connected to the plant room here in the Tetra building, which then connect them to the ATES wells. Like I mentioned, office buildings in the Netherlands often have a larger cooling demand, so they have a heat surplus. So after a couple of years running of the ATES system of the Tetra building, they found out that the yearly heat surplus of the Tetra building is about 50 megawatt hours. We can get another 25 megawatt hour from the PVT panels every year. So in total we can get 75 megawatt hours of heat. We use the heat pump to increase the temperature level. So in total we can get with a COP of 4, and then in total we can get 100 megawatt hours of sustainable heat to the ZZH building, the large facility building. So in total that reduces the gas reduction with over 11,000 cubic meters, which equals to 22 tons of CO2 every year. And also the electricity use reduces because the PVT panels also were supposed to produce electricity. Due to this pilot, unfortunately, they do not at the moment. So this is not actually the case in this pilot. But if they would have produced also electricity, then they would added another 3 tons of CO2 emission reduction. So these are the basic numbers. Here we have another PID. This is the existing installation of the Tetra building with 2 heat pumps. So the solar panels are here. They're connected in two parallel series of 2 times 60 tubes, and they're separated by this plate heat exchanger, which then diverts the heat into these into the existing system of the Tetra building. Well, as I said, they were installed just a couple of weeks ago, so we don't have much data yet, but this was the weekend after they were installed, the couple of days after they were installed, and well, they're producing nice thermal power to the Tetra building. What we're going to do now is we're going to monitor the system. We have some fiber optic cables which measure temperature over depth in between the wells, which allow then to see how the heat that we put in the warm well, how that propagates into the aquifer. Between 60 and 80 meters. There we have the aquifer, so we have a bit more thickness than in Italy, fortunately. With this DTS, we can see how much of how this heat is propagating. Interesting to see is that you see the distance from the well. That's only 30 meters or something like that. This aquifer that we have, there's a lot of space available there. So now we are only providing like 100 megawatt hours a year to this facility. So the actual energy demand of this facility is much larger than that. But we can easily increase the number of PVT panels. There's space enough available in the aquifer to increase the heat storage for facilitating the sustainable heat to the ZZH building. Maybe we need an extra well to meet the required capacity, but there's enough space available in the aquifer to do that. Little bit of outlook, because this is only one site, one building, and now we're collecting sustainable heat with the solar panels, but we can also get cooling capacity if the cooling demand is larger. One thing that I want to show here is all the ATES systems now, they all use a heat pump for producing the heat at the right temperature to the building. But this heat pump really uses a very large part of the total energy use of the ATES system still. So this is then, instead of gas, much better. We can produce this power sustainably by solar or wind power production. But yeah, we also want to drive electronically. This only you can only do this if there's sustainable power available for your use, but that's not yet the case. So it's very interesting to see how we can lower the energy use of the heat pump. And that's where this triplet system comes in, where we don't use the heat pump anymore. We want to get all the heat that we need. We want to get that from the solar panels, put that in this very warm well that we can use then to provide heating in winter. And in winter we can get extra cooling capacity from dry coolers, for instance, to get the cooling capacity that we need in summer. And you need this intermediate well for preventing to pollute your warm and your cold well when you're not able to produce the right temperatures at various times during the year. This is the ideal picture in the end. In the coming periods we will make more intermediate systems with the heat pump and extra dry coolers or extra PVT panels or asphalt collectors, for instance, just a heat exchanger in the asphalt to get heat or to get cold even in winter. That would be possible. So that's a little bit of an outlook how we can go from there. Also, other sources of heat we can use, just the geothermal heat production from the deeper parts of the earth. You have a very steady supply over the year from waste heat or geothermal heat. And if you want to supply that to municipality area, you can, in summer, you don't have a demand for that heat, so your surplus you can then store in these higher temperature wells, and in winter you can supply the peaks with that. When we start to use solar heat or solar wind power, then the mismatch becomes even bigger. You produce more in summer, so the need for storage becomes even much more, and these aquifers, they can provide this storage capacity to overcome the discrepancy in time between demand and availability of heating and cooling. So this high temperature, what we call high temperature, that's higher than about 30 degrees, which is currently in most European countries the limit that we are allowed to inject warm water. If you go to 40 or 60 degrees, we can directly supply that to buildings, so we can store much more heat in these aquifers. We can make the heat pump abundant, which is a very large benefit for the power grid as well. There are, of course, some technical challenges, but we're working on that at the moment. So that was what I wanted to share with you, and if you have any questions, feel free to ask.